So when we have variables that are ordinal or nominal, we use percentages or counts of how many people are in each category to describe those. We can use pictures, bar charts, and other forms of graphs in order to display those, or tables. When we have continuous or count variables, we can use means and standard deviations to describe those. And so these are the tools and techniques of descriptive statistics where we want to describe a sample. How many men, how many women, how many people of various ethnic or racial groups, what's the average age. These are the kinds of descriptive statistics that we generally see it presented in a table in our articles. But often we want to draw inferences about a population from the statistics, and this is called inferential statistics. Today we're going to go through a set of steps that form the foundation of statistical inference, and we're going to spend some time talking about probability and p-values to set a foundation. Next week, we're going to really build on this by talking about specific statistical techniques, regression and t-tests and chi-squared tests and some other things like that, and we'll talk about what those are. But this week, we're going to focus on what are inferential statistics and what is a p-value, and we'll continue this conversation next week. Inferential statistics and this thinking behind inferential statistics rely on this funny thing where we're going to think backwards. We have something called the null hypothesis and the alternative hypothesis. The alternative hypothesis is what you've been thinking about when we've been talking about hypotheses. So let's use cognitive behavioral therapy and depression as the example. Your hypothesis, if you're studying cognitive behavioral therapy and its effect on depression, is probably that the use of cognitive behavioral therapy, more cognitive behavioral therapy going up, depression goes down. So cognitive behavioral therapy reduces depression. That is your actual hypothesis. But in inferential statistics, we call that the alternative hypothesis. What you're going to actually test is not that hypothesis, ironically enough. You're going to test what is called the null hypothesis. The null hypothesis is that there is no difference between the treatment group that received cognitive behavioral therapy and the control group that didn't receive cognitive behavioral therapy. So what we actually do statistically is we say there's no difference between these groups. And because means of means are normally distributed, the mean of the control group and the mean of the treatment group should be normally distributed. And the normal distribution has a set of known properties. We know what the standard deviation is. We know what the mean of that population is. And so if the mean of the control group and the mean of the alternative hypothesis, which is what you're actually thinking of as the hypothesis, is if those means do not look like they come from the same normal distribution, then we reject the null hypothesis that there's no difference between the groups, and we accept the alternative hypothesis, or we find that there's evidence presented here in support of the alternative hypothesis. So it's a funny concept where we take the thing we actually think we're testing, which is does cognitive behavioral therapy work, we flip it, and we say, nope, cognitive behavioral therapy and the alternative aren't going to produce any difference in the level of depression. And we test that. We test whether there is the existence of there's evidence of a difference or there's evidence of no difference. And when we get the p-values, we're going to go back and back and back and back and cover this concept again and again, because this is the core of statistical tests and p-values. It also is the first step in inferential statistics, identifying what your alternative hypothesis is, and then specifying the opposite in the form of the null hypothesis, which is usually that there's no difference between the treatment and control group, or there's no difference between poor kids and rich kids, or there's no difference between abused kids and non-abused kids. And most of the time we don't think that's true, but it's the starting point for most statistical inferences, and it's called the null hypothesis. Once you decide on the null hypothesis, then we have to decide on the appropriate statistical test. We'll talk more about that next week on which statistical test and why we use various statistical tests. Step 3 is we decide on an alpha level, which we're going to talk about when we get the p-values. Generally, the alpha level we're going to talk about is 0.05. P-value less than or equal to 0.05 is the key metric for almost all of the statistics that we're going to review in this class. I'll explain what that means in a second. We perform the calculations and we obtain the statistic, and then we evaluate the probability of getting that statistic or an even more extreme value of that statistic. This is the definition of a p-value, and again, we're going to talk about that in just a second. And then we conclude whether the obtained probability is greater than the alpha level. If that is true, then we fail to reject the null hypothesis. Fail to reject the null hypothesis. Remember, in most instances, the null hypothesis is that there is no difference between the treatment and control group. There's no difference between poor and non-poor kids in terms of educational outcomes or food consumption or whatever. So if we get a p-value that is above 0.05, we're not going to reject the null hypothesis. That means our test, that cognitive behavioral therapy doesn't have evidence of effectiveness in this sample, in this study. We don't find evidence that there's differences in outcomes for poor and rich or poor and less poor kids. So failure to reject the null hypothesis happens when the value is above 0.05. If the value is below 0.05, we find evidence to reject the null hypothesis. Now, that doesn't prove the alternative hypothesis, and that's a key component. We can never prove the alternative hypothesis. We just have evidence supporting the alternative hypothesis. At this point, I imagine you're fairly confused, since this is confusing. One way of simplifying this is to take a research question that you have. So, for example, in your EBP1 project, you have a research question. Take your research question. Identify what the independent variable is, what the dependent variable is, and then specify what the alternative and what the null hypothesis is. So if in my example that I keep using in this class, let me switch to a different example. Maybe I have an assertive community treatment team, and I think my assertive community treatment team, giving assertive community treatment to people, will lower the rates of psychiatric hospitalizations for them. So my actual hypothesis is that assertive community treatment reduces hospitalization. That becomes my alternative hypothesis. My null hypothesis is that there is no difference in rates of hospitalization for people that get assertive community treatment compared with people that don't get assertive community treatment. So when I'm comparing the treatment group, which is assertive community treatment, and the control group, usual care, there's no difference between these groups in the rates of hospitalization. That's my null hypothesis. And I recommend that you do that for your own. I find that if you think through your own examples, these things make a little bit more sense. So just spend some time and figure out what the null hypothesis and the alternative hypothesis are for your EBP1 project. Can we talk about probability for just a second? Probability is a wonderful thing. Any of you are gamblers out there, you live and die by probability. Game players live and die by probability. So if we just take something like a simple coin flip, if I were to flip a coin 100 times, a fair coin, a quarter, how many times would you expect me to get heads? 50, right? 50 times heads, 50 times tails. So the expected value, the probability of heads is 50. That's my expected value. Now if I flip a fair coin over and over and over and over and over again, say I flip it 1,000 times, I can do that on a computer very easily, and I make my coin fair, I'm going to get a picture that looks like this. 50 heads, 50 tails. But what if I get a picture that looks like this, where there's 60 heads and 40 tails? That probably tells me, if I have a large enough sample, that something's a little off with my quarter, because it's not what I expect to see. I know what the quarter should do. I know that it should be 50-50. If it doesn't turn out that way, maybe it's just random chance. Maybe this just happens sometimes. If you only flip it 10 times, you're most likely not going to get 5 heads and 5 tails. You can go ahead and try it. Flip a coin 10 times. The vast majority of them are not going to be 50 heads, 5 heads, 5 tails. The majority of them are going to be something else, 6-4, 7-3, something like that. So probability tells me what should happen. As I move away from what I think should happen, Then I can start asking, okay, is it the sample size? If I only flip a coin 10 times, that's not enough. So maybe if I jack it up to 100, it'll get closer. If I jack it up to 1,000, it'll get closer. If I jack it up to 10,000, it'll be almost identical. At 10,000, I should see exactly, pretty close, rounding error kind of stuff to 50-50. Incidentally, that's why sample size, larger sample sizes, get us a better representative sample of the population, because we're more likely to have randomness, not introduce small little biases in our sample through random chance alone. So the randomness benefits from larger sample sizes. It's going to look more and more like the picture I want to see the larger my sample size. A p-value borrows on this concept that we've been talking about. There's a certain expected value. And if I don't get that expected value, then I'm going to say something's up. Now, most of the time, that something up is a good thing for us. We're actually wanting something to be up. We want assertive community treatment to reduce hospitalization more than usual care. But we're going to start with the null hypothesis that there's no difference. And if what we find is something that you wouldn't expect based on no difference, if the picture of randomness that we presented through the form of a normal distribution suggests that the value we found for the difference between the means of the usual care and the treatment group is way over here in terms of what we would expect based on probability theory, then we're going to say something is different about this group. And if we've done our study design correctly, the thing that's different is only going to be the introduction of assertive community treatment versus usual care. That's why all the threats to internal validity you have to be careful of, because those could be alternative explanations. And what we really want to do is we want to just isolate one thing, assertive community treatment compared to usual care.
Let's dive into this question of a p-value in a little bit more depth. And I know that this is confusing, so let's just take an example of cognitive behavioral therapy. The first thing we do is we set our null hypothesis with the expected value that there is no difference between cognitive behavioral therapy and usual care. So we say that the difference between these groups in terms of their level of depression after receiving usual care or cognitive behavioral therapy is going to be 0. That's what we expect to happen under the null hypothesis. But what if we find a value of 2? What if cognitive behavioral therapy reduces depression symptoms 2 relative to usual care? Well, that's not something we're expecting to get by just randomness alone very often. In fact, it's less than 5% of the time. That shaded area is all that stuff over there is our probabilities less than 5% of the time. Less than p equals 0.05. So this is the area, the critical area, the alpha region, where we're going to reject the null hypothesis. We're going to say randomness is not a good explanation for a difference of this size. Well, what's remaining? If we've done a good job with our study design and gotten rid of all those threats to internal validity, then the only remaining explanation is that cognitive behavioral therapy reduces depression more than usual care. And it's not just random noise that is the explanation for this. It's something systematic. In this case, the administration of cognitive behavioral therapy. But what if we find a difference of 1 or a difference of -1? Well, then we're going to say that randomness is a good explanation. We're going to find differences of 1 or -1 60% of the time, 40% of the time, 30% of the time, 20% of the time, 10% of the time, but often enough that we can't reject the null hypothesis. This doesn't mean that there isn't a difference between cognitive behavioral therapy and usual care. It just might mean that we don't have a large enough sample size. Or it might mean that the treatment effect isn't big enough for us to detect. Or it might mean that our measurement error is too big. Or it might mean that randomness is a perfectly good explanation, because there's always going to be a difference. It's never going to be exactly 0 between the two groups. Maybe one group had 2 people that were just more depressed than the other group, and that's why you found the difference. Or it could be a whole host of reasons why. But what we test in hypothesis testing, what we test with a p-value is this question. Are we likely to find a difference as big as we found by randomness alone? If we find that difference more than more than 5% of the time by randomness alone, then we're going to accept the null hypothesis that randomness is the explanation and that there's no difference between the treatment and control groups. If we find that difference, if we find a difference that's so big that we only find it with randomness alone less than 5% of the time, then randomness isn't a good explanation, and we're going to accept the alternative hypothesis that treatment is effective.
One of the key things to remember, though, is probability values don't tell us about meaningfulness of a finding. Just because the difference between two groups doesn't look like it's random difference. It looks like there might be something systematic going on that is differentiating these groups. It doesn't mean that's important. So let's say I have a assertive community treatment team and I'm counting the number of days that people in my assertive community treatment team were hospitalized versus the number of days that people in usual care were hospitalized. And I've got a very large sample. I've got 200 people in each group. And so I have a 400 sample study, 400 person study, which is a reasonably large sample size. So I'm going to be able to detect some difference. And I find that I saved over the course of a couple of years 3 days of hospitalization between the groups. Well, 3 days isn't nothing, but 3 days is probably not what you want to be spending millions and millions of dollars on, and assertive community treatment's expensive, so it's going to certainly cost some money. So even if I find a statistically significant difference, even if assertive community treatment reduces rates of hospitalization, that doesn't mean that reduction, just because it's statistically significant, doesn't mean that it's clinically significant. And what you'll often find in appraising studies is people have very large sample sizes in the hundreds or thousands, that find these statistically significant differences, but are those differences meaningful in a clinical sense? Now, statistics takes some level of training, and we're going to provide a small amount of training here. If you're interested in PhD courses, you can get a lot more training in statistics. We teach some wonderful classes here, for example. But it doesn't tell you anything. The p-value tells you nothing about the importance of the difference. That's clinical significance, and that you can have a judgment on. If, for example, I reduced each patient's days in the hospital by 3. Well, 3 days in the hospital per patient, that's a lot of time in the hospital. But over the whole sample of people, if I only reduce it 3 days, that's not so much. So the question of clinical significance is one that you can use your clinical information to judge. And I think an important thing about critically appraising studies that you get into is not getting caught up just in the p-value. The p-value tells you whether randomness is the explanation or whether randomness has a low probability of being the explanation. And we use that cutoff of 0.05. So 5 out of 100 times we'll accept as an error in this inference. But that's 5 out of 100 times isn't a very likely outcome. So those we're going to call not random. Everything from 0.06 all the way up to 1, we're going to say random chance is the best explanation for this. So it's only these little things over here that we're going to say random chance isn't a good explanation for. And we're going to use some inference to say, oh, it's cognitive behavioral therapy or it's assertive community treatment that causes the difference that's that unexpected. But nothing so far tells us whether that difference is important, and that's clinical judgment. And you can use your clinical judgment to say 3 days over 100 people in a couple of years in the hospital, that's not really that important. Maybe we can use these resources better elsewhere. Versus 3 days per person over those same period of time, that's a lot of hospital days. That's almost 1 hospitalization less per person, or a half a hospitalization less per person. And that's pretty significant. Maybe we should invest resources in this thing. So clinical judgment, based on the amount of difference and the importance of that difference, is separate from statistical difference, which is measured with p-values. So I want to separate those two things. P-values tell you whether random chance is the explanation. It doesn't tell you whether the difference is important. That's clinical judgment, and that's a separate form of thinking that you are just as informed about as the investigator is.